is a sort of a large, say, showcase on Moon and Mars data. So which types of data? Of course, I have not the ambition of covering the entirety of the data available for these two planets. And this is focused mainly on Mars and Moon because on Mercury, for example, you will have an exercise on Mercury too, next days. It applies to the same principles of data downloading. And but first, before starting to dive into the type of data, I would like to also put this small disclaimer. This is just related to the data useful for production of geologic maps. So there are many more types of data, but they will stick to the basics with those that you can use easily for doing geologic mapping. But of course, there is more. Anyways, you will have also this presentation in PDF afterwards. So let's start with the Moon. Okay, we have covered the Moon later today and early this afternoon. And I briefly show you the main missions from where you can retrieve data for image, photo interpretation, composition, and also topography, meaning laser or stereo coverage. That are Selene Kaguya from JAXA, Lunar Reconnaissance Orbiter from NASA, and Cube India and Clementine from NASA. Main repositories we are going to go to see how to retrieve Moon data is Google Moon for quick exploration, the Orbital Data Explorer from PDS, Pilot, Quick Map from LROC provided by the Arizona State University, Astrogeology, and JMARS. So again, a brief recap of the missions. You see, Lunar Reconnaissance Orbiter has lots of instruments. We will cover all of them, and also the other two missions, Selene and Clementine. We'll start from the LRO, Lunar Reconnaissance Orbiter, launched in 2009 from Cape Canaveral. It has lots of instruments. It has provided global image coverage with the LROC, Lunar Reconnaissance Orbiter camera, at medium resolution. We have also a very high coverage of high resolution in the same way by another channel of the LROC camera. We have a LiDAR-based topography from the LOLA.
I think we're seeing the slides. The slides are not going forward.
Oh, yeah, sorry. Let me try again.
So if you are...
Do you see the slides now?
Not yet.
Very strange. Let me try a different way. Okay, you should see my PowerPoint now. Do you see any of my screen?
No, at the moment, not. So we can take a little bit of rest to fix this problem, to let you fix a little bit this problem, just 5 minutes, and then...
sorry for that. Okay, I try to share my screen again. Let me see if it gets better. So, do you see my screen now?
Yes, Rick, now it works.
Okay, sorry. Don't know what happened. Okay, so we were briefly mentioning the Lunar Reconnaissance Orbiter, right? So a very important mission, high resolution data, imaging of the whole surface at the medium resolution from the rock camera, but also at a high resolution. We have a little LiDAR-based topography, so laser topography, stereo topography as well, so also from stereo pair images, thermal maps for cold traps. Harry Isinger talked about them this morning for permanently shadow craters, and also UV mapping, so in ultraviolet. This is just limited to the datasets used in photogeologic mapping. So we will go first and see the LOLA, Lunar Orbital Laser Altimeter. We talked about DTMs this morning, and this laser altimeter provided a global DTM topography at 118 meters per pixel. This means that each pixel has is 118 meters large, and of course the vertical precision is much higher. It's in the order of meters. And this provided the global topography of the moon, which is very useful to do, let's say, regional scale analysis or medium scale analysis and geologic mapping. Then we have the WAC, it's wide angle camera on board of the Lunar Reconnaissance Orbiter as well. And this is the global mosaic that was obtained by stitching 15,000 images acquired between in the time span of 2 years from 2009 till 2011. This is how the instrument appears on the, let's say, on the optical bench while they were tested and calibrated in the lab. And this is the global map that can also be downloaded as is in the USGS astrogeology repository, and we will see them later on. Of course, we have a wide angle camera, but we also have in the same instrument a narrow angle camera, which provides the other way around super high resolution images. Panchromatic means grayscale at 0.5 meter per pixel. And you see here an example of the Apollo 17 landing site with all the tracks by the astronauts walking on the surface of the moon or driving the rover on the surface of the moon, and all the instruments left on the surface of our satellite. So you see it's a huge telescope. It's mounted on this LRO as well. And just to give justice to this instrument, here you see something very spectacular from the NAC and narrow angle camera. You see a central peak. This is, I think, Tycho crater, if I remember correctly. And look closely. Okay, you have the central peak of the crater, impact melt all around, touching the rims of the central peak. If you see on top, here you have this small detail, and with a rock, you can spot a giant boulder on the top of the central peak, which probably is the result of the impact itself that created the central peak, and all the material that was thrown up then fell down and eventually ended up on the top of the central peak. So you see, you can still see a boulder. It's as large as a house or a large building. You see structures, fractures, and whatever, and you see even finer details like small boulders, regolith, and so on. So this is very, very impressive. And with this type of camera, you can, of course, derive very, very detailed geologic mapping. And also this camera has stereo capabilities, which means that together with this super high image resolution, you can also have high resolution DTMs on the order of 1 meter per pixel resolution, which is very, very good and can be used also for landing site evaluation, for example. Moving on to another mission, the largest mission of moon exploration since the Apollo was the Selen Kaguya, which stands for Selenological Engineering Explorer by the Japanese Space Agency. It's dedicated to the Princess Kaguya in the traditional tale, Japanese traditional tale, and it was active for 2 years and imaged the whole surface of the moon in stereo at the medium resolution. Here you see the very first image acquired by the Kaguya mission in 2007. And this instrument is the terrain camera, TC, which provided tiles, means like square tiles, frames of image at the medium resolution of, let's say, around 10 meters per pixel, which stands in between the LROC-WAC global mosaic at 100 meter pixel and the super high resolution of NAC at half a meter per pixel. So you see, you have different resolutions at different size, and these are filling the gaps one to each other, medium, high, and low. And also this terrain camera has stereo capabilities, which provided a DTM, not global, but almost global, only the poles were not included, at a resolution of around 60 meters per pixel. So again, we are improving the resolution of the laser altimeter. We are not as a high resolution as the ROC, NAC stereo images, but still quite high resolution for medium scale analysis, which is very, very convenient for geologic mapping. If we want to go and see also something about the composition of the moon, we can rely, for example, on Clementine data, which is a mission launched in the mid-90s, whose major discovery was the presence of water ice on the permanently shadowed crater for the first time in the South Pole, and contained a first version of the LiDAR, which was improved then by the LRO mission. Here you see a global map in false color of band ratio of the minerals on the near surface, near side of the moon. More specifically, this is a global mosaic available as is that we can download and put into our GIS, like QGIS. And this is a color combination between different channels. These band ratio are absorption bands that are related to, for example, sorry, this is in Italian, but I can translate for you. Low titanium and glass-rich areas, the red channels. So red channel, low titanium, and lots of volcanic glass. Green channel is sensitive to the iron content, and blue channel is sensitive to the content in titanium, for example, here and here. If you combine these together, red plus blue gives purple. And so where you have purple areas, you have a combination of low titanium, glass, and high iron content, and so on and so forth. And you will see it better while speaking about compositional maps and how to retrieve spectra. But nonetheless, this can also give you an idea on how to subdivide in major units the surface of the moon. And to have a look at that, there's the convenient tool of LROC Quick Map, which I will show you in a moment. Of course, this is a guide that is intended to be also available to you. And so there are some of the steps that I'm going to show you that are summarized here. But here I wanted to show you briefly how the quick map looks. You have all the references. It's just to showcase live how they appear if it opens up. So you have the surface of the moon, and here you have different buttons. You can switch projections, so you can move to orthographic, to stereographic, or to cylindrical projection in order to see the moon with different projections. You can have the 3D globe of the moon, and this is the very, very basic in order to focus on a specific area. For example, we can go and zoom in, for example, in the Copernicus crater here, just to locate our target of investigation. Then we have more, we have layers. So we can use different pre-compiled, pre-digested layers. There are lots of them. I cannot cover all of them, but just for you to know that they exist and you can consult them freely. So you have, for example, the Clementine iron abundance. If you toggle them, you see iron abundance in grayscale. Or you can toggle Clementine color ratio as before. So you can start seeing the different composition of this lunar linear side and how it affects also the Copernicus crater, okay? So all these layers, here you have the crustal thickness layer, for example. This cannot be downloaded from here, but they are available and you can consult them. You have titanium abundance in weight %, and so on and so forth. So this is a first, let's say, quick look of what you can see through the quick map at rock. Not only that, but you can also look for specific data to download. And you can do that by drawing with this icon, a search tool. You can point, you can draw an arc or a polygon. For example, around, we can choose polygon and draw around the Copernicus crater in order to start to see which type of data we can retrieve. As soon as I close the polygon with a double click of my mouse, you have the data values. So everything inside this polygon. But more importantly, you can search for products. You can search Mare units and cube observations, so the Indian mission who provided composition, or you can search, for example, NAC images, all of them, NAC DTMs, so the DTMs created by stereo pairs of narrow angle camera. And you see here, as if I choose this option, you have a couple of them. If you hover your mouse on top of this left table of content, the associated product will highlight for you. For example, let's see, I want to download this last one. So I click here and I have options. I have options to download it or to visualize it, okay? You can also gather regional mosaics. Here there are more. And again, there's the link to download them. 1, 2, 3, 4. You see, so this is specifically intended to gather and retrieve LROC products, but you can still consult other layers, okay, which is just the button at the top. You can also see geologic maps, for example, like a unified geologic map of the moon. I won't show you because you maybe don't want to see that before tomorrow, but you can do that. And other nice information. So this is covered in my presentation here, just for reference, where to click, what you can do or what you cannot do, and the types of products you can retrieve. For example, DTMs in this case. If you clicked on the links I showed you before, when you located DTM, you just will jump into this page and you can download the digital terrain model, orthophotos associated to the model at different resolution, slopes maps, shaded relief maps, and so on and so forth. So this is a very convenient way in consulting NAC images. So how to organize a GIS project? So Alessandro before talked about raster layers, on top of which we will make our mapping with our polygons and vector data. So the advice is to build, let's say, a context by using the low resolution data, such as the LOLA DEM or the Kaguya terrain camera at 10 meter pixel, or the WAC at 100 meter pixels. Just stay at the bottom, and on top of them, you can start piling up higher resolution images. And as you've seen before, higher resolution images can have limited coverage. So we need context for those high resolution images, and context is given by low resolution but much wider in scale images. So this is one way we can suggest you to build your mapping project, for example. So smaller scale, increasing resolution. And of course, increasing resolution means heavier data for the space mission to acquire, to downlink to Earth, and to be stored. So there are also limitations with respect to how to acquire data. And this is why high resolution data are very, very large in size and limited in availability sometimes. So the same can be applied for Martian data, okay? Martian data have lots of missions. These are just part of them, but let's say the most common used in the photogeologic mapping. So Mars Global Surveyor, Odyssey, Mars Express, Mars Reconnaissance Orbiter, but it's not limited to this. There's also, for example, ExoMars orbiting nowadays. and lots of repositories that we will see later on. You see here, there's even more. We go briefly again through these various missions. You see, Mars Global Surveyor ended up in the 2006, had on board MOLA. So it's like the LOLA, it's LiDAR, it's Mars Orbital Laser Altimeter, and the camera at high resolution. We have a Mars Odyssey, very, very old mission, but still ongoing, with the thermal camera that provided a global mosaic. Mars Express, again, still ongoing, with the high resolution stereo camera, also with color filters, and a spectrometer, Mars Reconnaissance Orbiter, which is a sort of a twin mission of the Lunar Reconnaissance Orbiter, with high resolution camera, spectrometers, and so on, and also the ExoMars mission. We will start again, as before, with the lower resolution data. And we do that by looking at, of course, the laser altimeter, so the MOLA. This is a video of the whole Martian globe taken with the MOLA. Here you see the South Polar Cap. Then we go northern. We start seeing, for example, the mid-latitudes, the Thaumasia region, then the Tarsis Montes. We go towards the northern pole, so North Polar Cap. You see the CO2 ice with all this swirly, let's say, shape. This is created with the laser shots of the MOLA laser altimeter. And of course, this is the Mount Olympus, Mons, for example. The Valles Marineris, we are just entering the Valles Marineris, 8 kilometers of depth, more or less. So you see lots and lots of features. So MOLA can be used for large-scale measurements. How are MOLA data collected? So this is how appears single MOLA orbits, single orbits of the space probe. You see here, these are small dots. Every dot is a laser shot. By putting together all these laser shots in different orbits, we end up in this data set. That's what you've seen before, straight onto a sphere, on the Martian sphere. This is the very first planisphere Mars with topography, some toponyms. You can, of course, derive the color-coded altitude, shaded relief maps, and so on. And on board the same mission, the Mars Global Surveyor, there was the MOC, Mars Orbital Camera, so one of the first high-resolution cameras orbiting Mars. It's panchromatic, so in grayscale, with resolution between 1.5 meters per pixel and 12 meters, so it was not bad for the early 2000s, with stereo capabilities, so we are able to generate DTMs with stereo observation of the MOC camera. And this is the coverage. So you see, it's not global.
Riccardo, you have been freezed.
Ancora. Sorry, it seems that I am freezed again. I try to switch connection.
Rick, now it works.
Now it's working.
Hello?
Now it's fine.
It's fine?
Yeah.
Okay, sorry. Did you see this, the coverage of the MOC camera?
Yes.
Okay, so
No, the coverage.
again,
no.
so very target.
Ah, okay, yes. Okay, we are seeing the Themis camera informations.
Okay, this is not good. So you should see the Themis camera now.
Yes, we
Okay.
see it.
Okay. So Themis camera is another imaging system that was orbiting since the early 2000s. That is basically able to observe the surface of Mars in thermal bands. So imaging, but also in the infrared. You see here some details about the camera. It was able to provide a global mosaic at 100-meter pixels. And the interesting thing is that we have a global mosaic both in the daytime and in the nighttime. And this is interesting because we can really distinguish the thermal response of the minerals or of the rocks between night and day. So how much heat they can retain or they can release. And now you should see the mosaic. You don't see the mosaic. Okay, now you should see the mosaic.
We see it. Yes, we
Yes.
see it.
Okay, sorry. Okay, this is the daytime mosaic from the thermal infrared camera. Okay, so you see clearly shapes, morphologies like crater lakes, inlets, outlets, some cliffs, some impact craters with terraces, and so on. You see illuminated areas, and of course, this is true because it's daytime. But if we switch to nighttime, we lose the information from the incident light, but we gather the information of the heat released during the night, during the Martian night, by the rocks. For example, about the ejecta rays of this crater. Okay, and again, we see more features like, for example, dune fields inside the craters. So the thermal emission camera gives information also on the granulometry of the objects you're observing. For example, bare rocks are able to retain and to release more heat during the night rather than, for example, dust that has a larger specific surface. So it tends to release heat much, much faster. As you go, say, on the beach, on the sand, it's very hot during the day, but as soon as it gets darker, the sand becomes very, very cold. And this is what you observe with the thermal camera, and I advise you to use that in order to get better information on how to trace geologic limits, geologic contacts, for example, like in the case of the ejecta rays of this crater. Okay, so you see, in the day it's different than in the night. In the day you see clearly the morphology, but in the night you see clearly the ejecta rays. So we go further and we go and see how the Mars Express high resolution stereo camera works. So we go a step further into resolution and camera performance. So this camera is a very, very complex instrument. It's made up by one nadir channel, so pointing just on the vertical of the surface of Mars. It has color filters, so blue, green, and infrared, 2 stereo channels, able to reconstruct the topography, and 1 super resolution channel. These are available in the PSA website, so the ESA archive, the Planetary Science Archive of ESA, but they are also stored or accessible from other repositories that you will see. And they appear like that. So, and they have this code here that represents the channel. So this is a blue channel. This is the D means DTM channel. We have 2 DTMs registered to different areoids and spheroids. The green channel, the infrared channel, the nadir channel, and the rear channel, and the red channel, sorry. So what is able to do HRSC? It's able to produce stereo topography in color of the surface of Mars at 12-meter pixel resolution, the images, at the 100-meter pixel resolution, the DTMs. When I talk about DTM resolution, I always refer to the ground resolution in terms of spatial resolution, not vertical resolution. Typically, vertical resolution is much higher than spatial resolution. Here, hopefully you will see, I have a small video that is showing what you can get from the HRSC camera provided by the Freie University in Berlin. So this is DTMs on the Valles Marineris and the Canor Chasma in colors. or at least in false colors, by combining the filters in the HRSC camera and draping these images on top of the DTMs obtained by the stereo capabilities. So you see you have different lithologies, different patterns, textures that you can use to map at a medium scale and to use in your geologic maps. Up to now, the coverage of HRSC, at least of the level 4 products, meaning products that are map projected with DTMs associated or to rectified image and color, is this one. So the green are the footprints of the coverage of HRSC nowadays. You see there are gaps here and there, like for example in the Tarsis, other areas that are much more covered, like a Valles Marineris, of course, all the dichotomy of Mars, the topographic dichotomy, the Gale crater, the Thaumasia region, and so on. So this is another instrument you can make use of in order to produce your maps. And nowadays, there's also a DTM, a global DTM, that is making use of the MOLA global topography that has a pixel size of around 400 meters, but where possible, it was merged with the 100-meter pixel resolution of DTMs from HRSC. So you can download a single file covering the whole surface of Mars that has the two types of datasets stitched together. So where there's high resolution, you can use it. Where there's not, you can use and rely on MOLA topography. Then we jump into the Mars Reconnaissance Orbiter mission, and we will look at one of the main instruments that, in my opinion, is a bit underestimated, but it's actually one of my favorites. It's the context camera. It's a panchromatic camera that is used to give context to the super resolution high-res image. As I told you before, super resolution has compromises and caveats on data volume in order to be acquired, stored in satellite, and transferred to Earth. So they need to be targeted and need to have context. This is the purpose of this camera. It has a resolution of 6 meters per pixel, more or less, panchromatic, and his footprints, his frame is 30 kilometers wide, and his length is variable between 50 and 300 kilometers. So it can cover quite a wide area at a high resolution. And nowadays, as almost a global coverage, means that almost the entirety of the Martian planet is covered by these 6-meter pixel images, which is quite impressive result. Additionally, although it was not designed to, since you have such a high coverage, some of these images are overlapping. And if the observation angles and the overlap is sufficient, you can create stereoscopic DTMs. It's not designed for that. You have to cherry pick the image pairs, but still you can try and do some very beautiful DTMs with CTX images. Data are provided raw. That means that you have to process them by yourself, or you can download them processed in 8-bit from the ASU website. I will show you later on. And the archive URL is this one. You can have a look later. This is how raw data appears when it's going to be ingested and calibrated into calibration pipeline. So this is the raw format coming out from the satellite. You see it's simply a matrix of pixels, a stripe of pixels with a lighter area at the center and the darker area around. It's called vignetting, means that the central part of the sensor is receiving more light information than the distal part. And you can, of course, calibrate the instrument knowing that it has this issue, and you can correct it. So by knowing that the instrument performance is that, we can compensate this effect and return these images that have all the grayscale nicely spread throughout the whole image. But it is not enough. So if you look closely, you have a vertical bending, okay, which are some errors in the detector that can still be calibrated and correct very, very nicely in this image. And you gather also much more detail by correcting these two types of, let's say, problems or things that to be taken into account while calibrating the instrument. And of course, you can map project this image and generate beautiful mosaics with lots of information. For example, you see this crater with these channels, dune fields, and so on and so forth. So this is very useful, and we will use it actually for the geomorphologic mapping on Mars. This is a very nice instrument, and inside these large frames at the high resolution, you can have the strips of high-rise, super high resolution. This is the global coverage, you see? Pretty impressive. All of these are all the footprints of CTX images, which is quite a huge data set to handle and to be managed. High-rise, super high resolution imaging experiment. I won't bother you with the details. You can read them by yourself, because I know that it can be tedious. But the important thing is that it has a ground resolution of 25 centimeters per pixel. It means that you can basically see the desk you're sitting in front of. If you were on Mars, you can see your car. It's designed for stereoscopy, so it has the ability to image the same site at 2 different angles in different orbits, of course, and is able to reconstruct topography at 1 meter resolution. Also with color filters, red, blue, green, and near infrared. Data are derived and calibrated. You can do it yourself, or you can download them from the website of the instrument, as well as the DTMs. And you can also ask for observations. So if you're interested on a particular area on Mars, and you really want to have a super high detail observation, you can register to the HiWish wish list. You can provide motivation for your observation, the time of the year, the illumination conditions, and you are selected, put it into a queue, and eventually your image will be taken. It might take a while, of course, because there are lots and lots of requests, but still you can try and ask your personal image on Mars if you need to work on that. Be aware that it might take some time, like months, so you must do it in advance if you need it. A brief hint on how the sensor works is very complicated, actually. It's not like a normal camera. It has 14 CCDs, so 14 sensors, each of them with 2 different outputs. The important thing is that the widest coverage of the image, this one, is covered by the red channel. So it's these filters here, okay, that are spanning throughout these images. So these filters are corresponding to these small framelets or these small stripes. The central ones, the 2 central ones, are also covered by blue-green filters and the near-infrared filters. This means that all together, this information, of course, needs to be put together. This needs to be equalized. And at the center of this red channel image, you will have also the possibility of color combination, obtaining very beautiful color images of the Martian surface. Typically, the SWOT size, so the size of this image is 12 per 6 kilometers in the red channel, and 12 by 1.2 in the central part with the colors. Here's some example of the performance of this camera. So here you see an area of Gale crater, and if you look closely, you will also see the presence of the tracks of the Curiosity rover. You see, Curiosity rover tracks where it was steering, and if you follow them, you see also the Curiosity rover here. This is the Kimberley outcrop, and you will go to see it also in the next days and in the next activities on the last day. And he also used for detecting surface changes. Imaging at a super high resolution portion of Mars in a certain time of the year can provide seasonal changes. These are the recurrent slope lineae that are flux of material, probably solid fluxes of material going down the slopes in the illuminated part of the craters in the Martian spring. I can give you more details on publications on that separately, but still you can detect surface changes, which is very convenient. And of course, putting that on top of DTMs, you can create very high detail models that can help you in your mapping. And of course, there are lots of DTMs already pre-done for you at the website of the HiRISE instrument. So you can simply go there, download them, download the authentified image, and you will get everything you need. This is the coverage. So you see it's quite a wide coverage, but you have to imagine it's almost 15 years that is, no, 13 years that is in orbit. Still, it's very targeted. Here is the Opportunity rover, landing site, Valles Marineris, the Gale crater all around here. So this is very, very targeted. And also the files are quite heavy. So summing up, difference in resolution affect also the mapping scale. You can go super high resolution with high rise. So maybe you want to map the boulders because you are mapping a landing site. You want to map the small layers, small debris, the ripples on top of the dunes. This is convenient using high-res images. If you want to use or want to map wider areas, you could use CTX, which is also almost a global coverage, but you lose some detail, although it's quite nice. You lose some details about the boulders, for example, the small, tiny layers, the textures of the materials, the small fractures, but still you see lots and lots of interesting stuff. If you need to widen your analysis and to, let's say, go broader and go regional scale analysis or medium scale analysis, you can rely on HRSC, which has double the resolution, double less the resolution of CTX. So you lose detail, but still has wide coverage. And if you want to do really regional scale analysis, like planetary scale analysis or 100-kilometer scale, you can rely on Themis, both in nighttime and daytime, also coupled with the MOLA topography, which is very convenient. Now, a brief hints on the ExoMars TGO, which is the ESA Roscosmos mission, which has the Cassis camera on board. It's orbiting Mars since a few years now. This is a resolution that is comparable or a bit better to the CTX, slightly better, I must say, with 4 filters. So CTX is panchromatic, Cassis is 4 filters. So like iRISE, infrared, near infrared, blue-green, and panchromatic. And also has a SWOT width, which is a bit smaller than CTX, but has stereo capabilities built in. And let's say, public release data can be accessed from the ESA PSA repository. This is one beautiful image of the coral crater by Cassis, and this is the coverage. So Cassis is also very, very targeted because it has color filters, it has stereo capabilities, so needs to be targeted to specific areas. You can find the images in the Planetary Science Archive of ESA. The ones with this locket unlocked means that you can download them, and you can request custom DTMs to the UNIPD enough archive. You can log in, register, and ask for DTMs on specific areas that can be taken into account in the processing pipeline and can then be generated for you. A brief hint, but the next days you will see it better on the Crescent. It's a spectrometers working with spectral cubes on Mars, and is able to provide high detailed information, for example, on oxides, on the presence of sulfates, of phyllosilicates, water alteration, and so on. And this is very, very targeted as well. So this is used most of the times in combination with high-rise images or high-rise with DTMs or CTX images, CTX DTMs. This is our advice on how to build a possible GIS project. So information raster layers to be put one on top of each other, starting with, of course, again, laser topography, daytime, nighttime infrared images, 100-meter pixels, then HRSC were available, DTMs, 100-meter pixel, then images, 12-meter pixel, then CTX Cassis 6 meters, and then super high resolution. This is basically what we advise you, because you need all the time, you need context to your analysis. So low resolution but wider scale might help you in retrieving the proper geologic interpretation. Then there are ways to visualize on the fly planetary data, and you might know it. Google Earth, limited to Moon and Mars at the moment, I will showcase briefly for you, but again, you will have plenty of information later on in my presentation. And if you open Google Earth, you should see it here now. All right. There is this top bar, and there's this planet icon here. If you click on the planet icon, you will have different options: Earth, Sky, Mars, or Moon. Let's go and check Mars, for example. If we go and check Mars, Google Earth will jump on Mars. You will see the Martian globe, and here the layers will change. Different table of contents. You can have place names, but you can have also global maps. So visible imagery, like in this case, you will have the colored Martian globe. Colorized terrain, you basically get the MOLA altimetric data draped on top of your Martian globe. CTX mosaic, if we want really to dive inside a specific area, and we want to check with details, we can toggle on the CTX mosaic, which is preloaded. It will turn on. It takes a while because it's quite heavy. And then you can zoom in, for example, in the Crommelin crater here. You can zoom in and have really a flavor of what you might want to start mapping. You see CTX images in grayscale are now loading. And this is very, very nice to have a look at possible mapping locations. Okay, then you have also, of course, if we zoom back a bit, as I told you before, the thermal images. So daytime infrared, and nighttime infrared, just to check day and night thermal response of minerals or rocks of the bedrock. This is just for you to start reasoning on how I want to build my map, if a place is interesting or not, before even starting to download the data in your computer, which can be quite an effort. You can have a quick look through Google Earth. There are also other layers, but one important thing is that you have also access to some of the spacecraft imagery. Okay, so the ones I've shown you before. For example, I want to have a look at the high-rise images on Crommelin crater. I toggle this on, and you will have the footprints of the high-rise images. And if you zoom in, you see, you have the footprints. You can click on them, and some information is displayed about this image. If you click on the image, like see this observation information page, you will jump into a browser, and you will instantly go into the location where that image is archived, and you are able to download the products like Quick Look, or also map projected real image at the full resolution, and so on and so forth. This is true also for CTX, for example. We just need to toggle on CTX layer, zoom back a bit, and you see all the footprints of CTX layers, or the mock, and so on and so forth. So you really can also have a look, for example, at Chrism. So you want to have a quick look at composition. You can click and jump into the observation information page, and you will get a flavor of the type of minerals you might expect in this location. This is just for you to start thinking of, am I doing mapping on this area or not? Is this interesting from a scientific point of view or not? So this is not the ideal place where to retrieve data, but you can still retrieve some of them. Of course, the best way is to process the data yourself. You can process the data yourself by using ISIS-3, which is integrated software for images and spectrometers by USGS Astrogeology. It's a processing, a calibration pipeline that is used also for mosaicing planetary images and is used for very specific purposes. It's Unix-based. It takes into account all the navigation kernels of the space missions. It's not the most friendly software, I must admit, but you can reach very, very nice results and very, very refined results. But since this is not the aim of our course, and this can be very, very much time consuming, we can rely also on different repositories where you have the data that you can retrieve without any processing effort or with minimum processing effort. So we will start with the PDS, Planetary Data System from NASA. The PSA is the Planetary Science Archive of ESA, and then other ways to distribute this data in, let's say, a more GIS-friendly way, GIS-friendly way. So the first one is the PDS. You can just click on this link, and then you can search your target planetary body or mission. You will jump into a download screen where you can select your products. The Planetary Science Archive of ESA works in the same way. So you have either FTP server download, so you have to know the specific, say, observation parameters of your image, or for some missions you have map view. But I will want to focus attention on the orbital explorer, which is still part of the PDS geoscience node, but is another way to distribute the data, which is a bit more user-friendly. And I will show this to you interactively in a second. So, PDS geoscience node, orbital data explorer. So here you have 4 major, let's say, terrestrial planets. This is limited, of course, to this. So let's say we want to download Martian data. We click on Mars. We end up in this page. We have different toolbars here at the top and different way to locate our images. The map search is the most intuitive one. Here you have base maps. Base maps, it means it's the base layer on where you will look for your images. You can select different layers. For example, I want to see the MOLA shaded relief topography because I find it more useful. And then we can zoom in wherever we want. And we can select specific locations. We can pan, of course, we can zoom. We can select a specific rotation by a rectangle or by a polygon. And we can see here, we can toggle this option if we want to display all the products in this area we are marking, or just the products in the selected area. I will click this one because then I can draw my polygon, for example, in this area, if it allows me to do that. And of course, in the right bar here, there are all the missions. Let's say we want to retrieve Mars Reconnaissance Orbiter. We want to retrieve high-rise DTMs, okay? So we select in the table of contents the products I want to retrieve. I click here because if I toggle this off and toggle this on, I will have all the products on the whole surface of Mars, and it's very, very intensive in terms of downloading this on the fly. So it's better to keep this on, select the product, and then with the polygon, just go around. You see the area you want to download the high-rise DTMs, for example. And inside here, I will have the footprints or the data products available, okay? So then I just need to click to view my search results that are these ones. So these are all the DTMs I found in my polygon. I can sort them, I can check all of them, and I'm putting them into my cart. It's like go shopping for satellite images without paying, which is convenient. When they are in your cart, you simply go in download here. And here you have a sum up of all the products you want to download, okay? These are, for example, additional products that you might do not want to have. And here you have the estimated data volume of the products of our, for example, DTMs I selected, which is 7.7 gigabytes. And it will take 2.14 minutes, hours to get them. So there are two ways to do that. Either you continue and you provide your email address, and after 2.5 hours, more or less, you will receive a link where you can download your images, or you can use this text-based for the ones of you that are used to use Linux or command-based interface. You can download simply the URL list, and you can put it in your terminal. You can do wget and get all the data downloaded into your computer. This is very convenient, you see, and we have our map search. There are lots and lots of products. For example, HRSC, derived products like DTMs from HRSC. We see all of them all around the Martian globe. We can select them, click to view, select the ones we want, and download them. So very, very convenient way of retrieving planetary data. This is the Orbital Data Explorer. And in my PowerPoint here, we'll have all the process you have to do to retrieve and download data. But I just wanted to show you live because it's better. Then we have the Pilot. Pilot is another way to get data. It's basically a USGS metadata-based browser for images. So not for spectra, but just for images. And you see here you have, in this case, basically all the solar system. So in the ODE case, you have Mars, Moon, Mercury, and Venus. Here you have also asteroids, moons, and so on and so forth. So we quickly jump into this, this system. And for example, let's go to the moon in this case. So we can select the moon here. If I select the moon, I will have a list of all the instruments available for me to have a look. Let's say I want to do a rock NAC, for example, left. So I click the rock NAC and I can go to the map search. Again, here I have my base map, which is loading. There are different layers here. If you go on the top right, we can choose whatever we want. Let's see. We want to go again to the Copernicus crater, but we not necessarily we need to know the toponyms or where there are the exact location of the places, because here you have a feature finder below. So you can choose craters. For example, I want to go again to Copernicus. So I go here, select craters. Takes a while because now it needs to load the database. And then here on the right, you can select the crater. It's in alphabetic order. We can go down. We can locate Copernicus, like Copernicus. Here, click on Copernicus, and then you will jump automatically to Copernicus crater. And also you will have on the right side all the rock images inside the Copernicus crater. If you toggle this on, you will see this button, this yellow button. You will see the footprints of the images, which is quite a lot, you see, inside the crater. You can order them, ascending, descending, by illumination conditions, and so on. You can select all of them if you go and click here, or some of them, like I want just 1 and 2, and I want to display just the footprint of this one and of this one. Okay, so you see these are these two images. There are different options. This one with this small blanket here is info, and here you have all the information on the illumination conditions that you asked me this morning. So which is the incidence angle, which is the latitude, which is the phase angle, the resolution at the ground of the image, and so on. You can get all this information inside here. You can select them, you can click on this small arrow, and you can start to download them. There are several ways to do that. You can download a CSV file, like a table file, with all the URLs to download your data. Or you can do, again, a script with the wget calls for the ones familiar with the command line interface, or you can go to projection on the web. If you go here, you need to be registered, but I can show you. You jump to a service which is enclosing, let's say, encapsulating ISIS, this software for calibration pipeline and map projection, where you can basically order your images. You can ask for specific projections, and you will again end up with your download list in your email for you to download. So let's say you want a polar projection or sinusoidal projection and so on. For the moment, it doesn't seem to work, but I know that there were problems also on their server side, because yesterday none of this was working. But I have it here. You could see it later on in my presentation. Moving on, there's also another repository, again from the USGS astrogeology, where you can download not images, like single images like before, but you can download predefined products. For example, let's say I want the global mosaic of Mars in shaded relief. I want the global WAC mosaic of the moon. And this can be downloaded from the Astropedia, USGS astrogeology. It's here. You have data and tools. You can go inside. Hopefully it works. Yeah, like terrestrial analog landing sites and so on. And inside this Astropedia, you can download not only these mosaiced ready products, but also geologic maps, specific databases, for example, crater databases, volcanic vents databases for Mars, dune databases for Mars again, and so on. So here there are also vector shapefiles to be loaded into your GIS, available, produced by USGS, with all the reference and explanation of how they were generated, by whom, and what do they mean. So here you have mosaic products and also geologic maps, historical geologic maps, and also databases. Like in this case, you have original files. For example, for this global dam, you can download the original file, or you can see a sample. So this will show you how this data set looks like, okay? In different formats, TIFF or PDS or IGES3, and you can also see the metadata. Then we will jump again into QGIS again, just for a second, before leaving the stage again to Alessandro, because there are also other ways to retrieve information. So the WMS, it's a web map service. So let's say you don't have much disk space in your computer, but you have a good connection. You can use a specific database, which is this one. It's linked in the slide. You can stream on your computer through the internet base maps of different planetary bodies throughout the solar system. Okay, you have the list here, and it's very easy. You need to open QGIS. You will have all the instruction. I will just want to show you live how it works. Okay, you open your QGIS main interface. You go to layer. You add layer, and you add a WMS layer, okay? A web map service. You have a window popping up, okay? You click on new, and this appears. This pop-up window appears. Here it's very simple. You go to this page with all these data sets. Let's say we want, for example, to get the, I don't know, Europa, Galileo, or yeah, or Callisto. So you can go, you can copy this link, right click with your mouse on get capabilities, copy the link, then go into your QGIS. You go and type Callisto here, and you paste the link. Okay, you simply paste the link. You click OK, and you click connect. Here, if everything is going on correctly, you will have a list of layers, and then you simply connect, and you simply close. If you go here on your databases bar, you will have WMS. You can click on this arrow, you can expand them. You will have a list of what's, for example, I added Callisto now. If you click again, you have WMS Callisto server, and here a Callisto global mosaic. You simply double click on it, and it's going to be streamed into your computer. You can zoom in, you can zoom out, and you can start mapping, for example, the surface of Callisto. Okay. There are those for Mars, okay, with much more layers. You see here, for Mars, there are HRSC, MOLA, shaded relief, topography, TEMS data. So we can, for example, remove this. And we can add MOLA shaded relief. And then you get the planisphere of Mars streamed into your computer, and you can start mapping on that. Then there is one last thing, which is the Mare Lab. It's a Caltech repository, which has the global CTX mosaic of Mars. It can be streamed in the same way on QGIS. It's the global mosaic, says 6 meter pixel resolution. You just need to download a simple file, which is linked in this location. It's a file that you can drag and drop into your window, and then you can also have the streaming of CTX mosaic. And of course, from this repository, you can also download tiles, like square tiles of CTX pre-created mosaics, like this. You can select, click the tiles, and you can download them. And also, this applies for high-res images. So you see, there are actually lots and lots of ways on how to retrieve data. The same data can be stored in many places. Every place has this specificity. One is more related to optical images. One is more related to databases, shapefiles, geologic maps. Another one is related to single files. You can process them or can download them raw and process yourself. It depends on your needs. So my aim with this long lecture was to give you an idea of the products you can have, for example, on the moon of Mars, but this can be applied also for Mercury. It's the same. And also the main places where you can retrieve data. I know it's a lot of information, but at least you have a flavor on where to have a look for getting data for your projects.